In this video, we are going to give an introduction to pericyclic reactions. Understand that pericyclic reactions are going to be reactions that either form a cyclic system, as you can see in the examples number 1 or number 2, or it's going to have a rearrangement. Now, understand that when it comes to pericyclic reactions, even though the book discusses the 3 that are illustrated in the slides, which include cycloaddition reactions, electrocyclic reactions, and sigmatropic rearrangement, we are only going to be focusing on the first one, which is the cycloaddition reactions. As you can see here, in the cycloaddition reaction, we're going to have a diene interact with an alkene, and we're going to be synthesizing a cyclic alkene. Let's start talking about the logistics of this cycloaddition reaction. So, understand that this is common to all pericyclic reactions, but we're going to focusing on the first one, as I just mentioned. The reaction mechanism is actually concerted. So it means that it proceeds without any intermediates. We don't even have the generation of radicals in it, okay? The mechanism involves a ring of electrons that are going to be moving around in a closed loop. Understand that even the transition state in these systems is going to be cyclic, and the polarity of the solvent generally has no effect on the reaction rate for the reaction. And the transition state has little, if any, charge. Because remember, it is all happening at once. We have electrons that are going to be cycling within a ring system. So, the particular cycloaddition reaction that we're going to be focusing on in this chapter is called the Diels-Alder reaction. And the Diels-Alder reaction is actually very useful because, as you can see, we're going to have a 4+2 cycloaddition reaction, which means that we're going to have the diene interact with an alkene, as I just mentioned, and then whatever group is in the alkene, as you can see, is going to be part of the ring system of the cyclic or cycloalkene. Now, as you can see, like all pericyclic reactions, when it comes to the mechanism for the Diels-Alder reaction, it's going to be concerted. There's a particular way in which we write the curve arrows for the formation of that product. We always initiate the arrows, okay, from the alkene, okay, into the diene. Then the second arrow is going to be from the bottom part of our diene into the sigma bond that was in the diene. I'm just going to highlight this. So this arrow is what forms the carbon-carbon double bond that we see in our product. And then, as you can see, the electrons that we have in that other portion of the diene is what makes a sigma bond. So again, as you can see here, we're going to be forming, which are labeled in red, 2 single bonds, and we're going to be generating 1 double bond. And overall, the whole molecule is going to be cyclic. Now, understand that if we look specifically at the energy diagram of the reaction, it's not going to have 2 peaks. It's just going to have 1 peak. And the reason is because overall in this reaction, we only have 1 transition state. And in this transition state, as you can see, I'm just going to redraw those arrows. This forms a single bond, this forms a carbon-carbon double bond, this forms the next sigma bond. What we have illustrated in the dotted line is the formation of the cyclic system. And again, that is the transition state, and that is what leads to product. So that's why when we look at the energy diagram, we only have a single peak designated to the transition state for the reaction. Now, Understand that when we have these Diels-Alder reactions, most of them are thermodynamically favored at low and moderate temperatures, okay? And the product stability actually dominates. If the temperatures are raised above 200 degrees Celsius, then the retro-Alder, Diels-Alder can predominate, and it's because of entropy factors. But again, in this chapter, we're just going to be focusing specifically to the Diels-Alder reaction, not the retro Diels-Alder. So, in order to understand the Diels-Alder reaction and the stability overall of the reaction, then we actually need to think about the delta G for the reaction. Remember that when we have the delta G of the reaction, we are going to be looking at different components. The delta G of a reaction is actually the Gibbs free energy, and there are two components to it. There is an enthalpy term and there's an entropy term. Okay, now understand that when it comes to the delta G, specifically of the reaction, that sign of the delta G must be negative for the equilibrium to favor products, okay? So to determine the sign of the delta G, there are, as I just mentioned, the two terms. Now, we are going to consider first the enthalpy term, okay? And there are going to be many factors that contribute to the magnitude of that enthalpy change or that delta H, okay? But the most dominant factor is going to be bond strength. Remember that in the Diels-Alder reaction, overall, we are going to be breaking a series of bonds and we're going to be generating a series of bonds. Specifically, during the process of the formation of the reaction, so when it first occurs, we are going to be breaking 3 pi bonds, okay? Overall, in the reaction, we are going to be forming 1 pi bond and 2 sigma bonds. As it was discussed in first semester organic chemistry, remember that when it comes to bond strength, sigma bonds are actually stronger than pi bonds. So when we look at that enthalpy term for this process, because we are generating 2 sigma bonds, understand that this process is going to have a negative value. So the reaction is known to be exothermic. Now, when it comes to the entropy term, understand that the entropy term, which is the delta S, should be negative, okay, for 2 molecules when they combine to form a single product, okay? Now, in this case, when we are actually taking into account that entropy term, there are actually 2 main things that we are going to be looking at. First, the 2 molecules that are going to be joining together. As I mentioned, they're going to form a single product, okay? And then the second one is that the ring is going to be formed. Now, understand that in this process, each of those 2 factors are going to be decreasing entropy. And remember that entropy is going to be the disorder that is going to be present in the molecule. So that's why when we are looking at the whole system, that contributes to a negative value in that delta S. And since temperature is always positive, therefore that minus T delta S term is going to be positive also. Now, when we look at the delta G overall in the reaction, as I mentioned, the enthalpy term is going to be negative, But again, because we have to take into consideration the temperature along with the entropy term overall, even though we think that the delta S specifically is minus, when we take into account the temperature overall, the entropy term is positive. So for the Diels-Alder reaction, because the enthalpy term must be larger than the entropy term for the reaction, then only when that happens, as you can see, the reaction is going to be favored. So at very high temperatures, because the entropy term is going to be opposing the formation of the product, that's why the retro Diels-Alder is going to be favored. Now, the ideal temperature for this reaction will be between room temperature to 200 degrees Celsius. Now, when it comes to the Diels-Alder reaction, understand that there's going to be two components to this reaction. The diene, and then the alkene is going to be called a dienophile. Understand that the dienophile needs to possess an electron withdrawing group, or the reaction will require higher temperature in order to occur. So when, as you can see, we have just butadiene with an alkene, and they react with one another. Even when you heat it to 200 degrees Celsius, the percent yield is only 20%, okay? And remember, once we increase the temperature, the retroaldo is going to be the one that takes over. So understand that adding that electron withdrawing group is going to be much better for the reaction to go forward. So when that electron withdrawing group is attached to the dienophile, then the reaction generally goes spontaneously. And as you can see here, when we compare this butadiene and we reacted with this alkene system that contains a aldehyde, which this is just considered an alpha beta unsaturated system, understand that the reaction goes to 100% again, because we have that electron withdrawing group in our dienophile. So as you can see, to give you some examples of electron withdrawing groups that can be part of the dienophile, here we have a ketone. If R equals H, then that is going to be an aldehyde. So R equals alkyl in order for that to be a ketone. We can have an ester, as you can see in the second one. We can have a carboxylic acid, and we can even have a cyano group. Once those are incorporated, as you can see, the reaction it happens spontaneously.